In this video, I want to do a slightly more involved parameter estimation problem, one in which we have two parameters we want to estimate, namely the slope and the intercept of a straight line. And so our data set is going to be the following. Something like this. And then we want to fit the straight line through the data. And we're going to assume that there's no error in the xi's. So the x sub i's, these are known exactly. But the y's have errors, so the error will be this deviation here. These are known as the errors. So all the error is in the y direction. I have n data points. And we can express these in vector notation as follows. And so we're going to be assuming that our model is of the following form. Y is equal to m times x plus b times 1, where this is a column vector of 1's plus some error vector epsilon. And I guess I can specify what 1 is. It's just a column vector of 1's. And this is an n by 1. And epsilon, the errors, is a column vector of epsilons. And these epsilon sub i's are normally distributed with mean 0 and variance sigma squared. And they're assumed independent. So in other words, covariance of epsilon I and epsilon j is equal to 0 if I is not equal to j. Sometimes we use this Kronecker delta notation and we write it like this, delta ij. And this delta ij is equal to 1 if I is equal to j and is 0 otherwise. So like this. Times sigma squared here. I need to add the sigma squared. Because the covariance of epsilon I with epsilon I, the covariance with itself, is sigma squared. That's the variance. Okay, we're going to use this fact when we write down the likelihood function. That's why I went through all this. So maybe we can write down the likelihood right now. Remember, the likelihood is the probability of the data given the model. But what do we know? We know something about the probability of epsilon. And so that's what we're going to use to find out what the probability of y is. We can either write this as a multivariate normal distribution with a covariance matrix given by this expression, or we can write it as the product of univariate probability normal distribution. So we'll first write it as the product of univariate distributions, because I think that's simpler, and then we'll write it also as a multivariate distribution with a special covariance matrix. So because all the epsilons are assumed independent, this joint probability for all the epsilon factors into the product of univariate normal distributions for epsilon 1 up to epsilon n. And this means that I can rewrite it like this. These are the normal distributions for epsilon 1, epsilon 2, and so on, with variance sigma squared, and then I can simplify this. So I have n factors of sigma, I have n factors of root 2 pi, and then the product of these exponentials is the same thing as the exponential of the sum of the exponents, and I factored out the 1 over sigma squared, so I'm just left with the epsilons. And this then can be written as this sum of the epsilon squared is like the dot product of the epsilon vector with itself, so that's epsilon transpose epsilon. Alright, so this was where I've written this out by using the fact that the components of epsilon are all independent. Now I could also write it directly as a multivariate normal distribution right from the outset, and that would be the following. And here I'll write down what the covariance matrix is. So this is the general form of the multivariate normal distribution with a covariance C. So what you get a C inverse sandwiched between the epsilon transpose epsilon. This C inverse matrix is also known as the precision matrix. So C is the covariance matrix, and W equal to C inverse is known as the precision matrix. Now for our particular problem, we know that all the epsilons are independent, and so the covariance matrix takes on this special form. So if I take epsilon with epsilon transpose, I don't get a scalar, I get a matrix, and it's the product of all pairs of epsilons with itself. And if I take the expected value of that, what I get is the covariance matrix. And then, because the epsilons are independent, these off-diagonal elements are all assumed to be zero. The only one we're left with is the variances, or the covariance of epsilon sub I with itself, which we've said is equal to sigma squared. So this is the same thing as, and this can be written more neatly, just like this, times the identity matrix. This is the n by n identity. And then if now I can compute the precision matrix, which is C inverse, and what we get so it's just 1 over sigma squared times the identity, right? Because the inverse of the identity is the identity. The identity is its own inverse, and then the inverse of sigma squared is just 1 over sigma. So this is the precision matrix for our special case where the errors are assumed independent. All right, so that was a big aside on introducing these covariance matrices. And now we're going to use that to write the likelihood function. So remember, we're trying to fill out this expression here, the probability for y given m, b, and sigma squared. We have y is equal to m times x plus b times 1 plus epsilon, which means that we can rewrite it like this. Epsilon is equal to y minus mx minus b1, which we can rewrite like this. Where here we've created a matrix whose first column is x and whose second column is 1s. So in other words, this matrix here, maybe it doesn't look like a matrix, is just this matrix. And this has a name. We're going to define it, call it A, and it's the design matrix. And so here I can rewrite this as y minus A, and this, I'm going to name this vector beta, where beta is just the vector of parameters. So to fill out the probability for y, I can write down the probability for epsilon. And I should evaluate what this determinant of C is. And so the square root of the determinant of C. So we just get the factor of sigma to the n, which we expected from our previous expression. Right, sigma to the m. So the thing to remember is this determinant of a matrix multiplied by a scalar. When we pull it out, we get that scalar raised to the power n, where n is the dimension of the matrix we're taking the determinant of. So I was an n by n, so we get n factors of sigma squared we can pull out of the determinant. And over here we can also substitute in the fact that w is 1 over sigma squared times I, to confirm that in the end this is the same thing we had before. It's the same expression we had before. But what we're going to do now is we're going to substitute in, where we see epsilons in this expression, y minus ab. So the probability of y minus ab is the same thing as the probability of y, because a and b are fixed and known, so they don't vary, because we're conditioning on those values. And here I can pull out the factor of 1 over sigma squared. And epsilon is y minus a beta. And then the identity, which is not going to change anything. Alright, so this is our likelihood function. Now I spent a lot of time getting here, but in fact we could have just written it down very quickly just by writing this normal distribution with E transpose E is the same thing as this expression. So this is the likelihood function. For the prior, we're just going to choose a simple one. In other words, we're assuming that the prior probability for the components of beta, namely m and b, is flat. It doesn't vary, doesn't depend on those parameters, and that the probability is flat in the logarithm of sigma, not in sigma itself. So we're going to assume that there's the same amount of probability between 0.1 and 1, between 1 and 10, 10 and 100, and so on. And so because the intervals are getting smaller and smaller as we approach 0, for example, 0.01 to 0.1 has the same amount of probability as between 0.1 and 1, and between 1 and 10, and that means that the density in terms of sigma has to go up as 1 over sigma as we approach 0. But this is a flat prior probability in the logarithm of sigma, which better reflects our knowledge about sigma. Sigma is a positive number, and if I told you that the variance of a quantity was 1,000, okay, and then I tell you, well, actually it's not 1,000, it's 1,005, then that seems like a pretty minor difference and you wouldn't think much of it. But if I told you that the variance was 0.1, and I said, no, actually I made a mistake, it's 5.1, now that's a huge change when we went from 0.1 to 5.1. That change is 5 units, but it was the same size as the change from 1,000 to 1,005. So you can see that our knowledge about the variance is reflects our expectation that it'll be flat in logarithmic space. So it's the relative changes that matters more. Anyways, we have this prior, we have this likelihood, we can combine them to get the posterior. Okay, and now I'd like to talk a little bit about the geometry of this quantity here that we see inside the exponential. So remember that A is a matrix whose columns are the two vectors x and 1. And so with these two vectors I can make a plane, and I can draw the two vectors. These two vectors live in the plane. We call this plane the model space. And it's two-dimensional space, whereas the data, y, lives in n-dimensional space. So this is a thin sheet inside an n-dimensional space where the model lives. And if I pick a point, any point on this plane, then that's a particular model. That would be, this vector would be a times beta, because it's a linear combination of x and 1 that brings us to that point. if I drop a perpendicular onto this plane, the point I get over here, that's the projection, and that will be give me this vector, which is a times beta hat, where beta hat is the solution of the normal equations that we get when we want to find the projection. So beta hat is the solution to A transpose A is equal to A transpose Y. It's the solution to the normal equations. And then this vector from here to here, that's the error vector. And that one is equal to Y minus AB, right? If I go from Y and then I subtract AB, which is going that way, end up here, which gives me a vector which is the same as the vector E. So this is Y minus AB. So this expression here is just E transpose E. And now we can use the Pythagorean theorem. If I write this vector over here and this vector over here, I can say that E transpose E is going to be the square of this vector plus the square of this vector. So what's this one? This vector here, maybe I need a colored marker. This one is the same thing as this minus this one, right? If I go from to AB and then I subtract AB hat, I'll end up over here. So this is A beta minus A B hat is equal to A beta minus beta hat. And this vector along here, this one, is the same thing as Y minus A beta hat, right? If I go here and then I subtract this vector here, I end up with a vector which is parallel to this vector over here. So this is Y minus A beta hat. And so that's what we do call completing the square. So we can write E transpose E is equal to the square of this quantity plus the square of this quantity. And the reason there's no cross terms between these two is because this vector here is perpendicular to the plane. So that's why we don't get the cross term. So we get two nice squares that doesn't involve betas on this side and y's on this side. Okay, and I can substitute this in here to rewrite the posterior in a neat way. So I'm going to use this expression, substitute in here. So first let's copy this down. This quantity here is this quantity. So this becomes and I'm going to take the transpose this time. That's the first term and then the second term. Alright, so this is the posterior. And now if we look at this expression, it's easy to see what the most probable value of beta is. This thing is going to be maximized when this exponent is minimized. And this is the sum of squared terms. So this is always positive. And this is the sum of squared terms, which is also positive. So the smallest value this can have is 0, and that's going to happen when beta is equal to beta hat. So beta hat, which is the solution to the normal equations, is going to be the most probable value of beta. I should try to marginalize out what sigma is to find the posterior probability for beta alone. And this is a multivariate student t distribution for the two components of beta. And so we can use this function to find the error bars on the parameters beta and beta hat, and also to find their covariances. And in fact, from here on in this page, there's nothing we've done that is limited to the case where A has only 2 columns. It could have an arbitrary number of columns. So as long as the model is linear in the form that the data Y is modeled as a matrix A of known components times a column vector of parameters, then the linear regression model is going to have this form, and this is going to be the marginal joint posterior probability for beta alone after integrating out sigma. And if we cared about the value of sigma, we could integrate out the components of beta to get a posterior probability for sigma alone if we cared about that. It's also possible to integrate out one component of beta and get a univariate probability distribution for M alone or for B alone. But I think it's going to be enlightening to look at the joint distribution for the two components of beta, and we'll do that in the next video in MATLAB.